Okay, everybody. It is my great pleasure to welcome you to Edinburgh for this, what appears to be a lovely set of talks we're going to see this week. I asked Dan what one says at the start of a conference like this, and he told me to just keep it as brief as possible. Do that. Just very briefly, the funding for the conference comes from 4 different bodies: the ERC, European Research Council, the ICMS, who, in addition to hosting, have provided us quite a lot of funding. They're funded through EPSARC, which is the British equivalent of NSF and ERC, and then the NSF is providing funds for many of the American-based participants. Last week we had a fantastic summer school, so I want to thank all the speakers there. So we had a series of lectures introducing the double affine Hecke algebras that clearly play an important role in all of mathematics, in particular many of these talks. We had an introduction to factorization homology. So DAHA was Monica Vezirani. We had an introduction to factorization homology by Hiro Tanaka. We had an introduction to shifted symplectic structures by Pavel Safronov, and to Homfley homology by Tina Kanstrup. And then we had a series of other lectures triangulated around those. So I think the context is sort of established. That said, many of you have said that you plan to keep it a bit colloquial in your talks, and that's much appreciated. There's a lot of people from different backgrounds that have agreed to come, and I'm sure they'll appreciate you explaining the points over the details. Okay, so a few bookkeeping things. The weather is nice today. The people last week will attest that it was equally nice all of last week. If you wish, you can. There's a courtyard. If you exit the building, you go right and then left. There's a university courtyard there with trees and grass. It's a lovely place to have a picnic lunch if you want. You can grab your food and take it. Otherwise, there's the tables here, and I'm told that we can use the common room this week. It's usually reserved for graduate students, but this week they're allowing us. Let's see. Slides. If you're taking slides, you'll be getting so all speakers this week will receive an email from Sasha Shapiro, who's volunteered to organize the slides. So you can either email them to him or volunteered. You can either email those to him in advance or just seek him out. Sasha, can you just raise your hand so everybody sees you? So if you just find him right before your talk, he'll help you set it up. Also, this thing hanging from the TV, there's a little camera. You can't see it if you're sitting behind it. It's recording all of the talks, but not everybody has agreed to have their talk published, of course. So what's happening is that's feeding directly to the room across the hall, which is just an overflow room. We technically have enough seats for everybody, but if you feel claustrophobic or if you want to be able to sort of tune in and out, there's the overflow room next door. I just want to assure everybody that the cameras are rolling all day on a live stream, but only those who have consented would have their videos uploaded, and in fact, you can change your mind afterwards if you let the secret out. Okay. Andrea, can you just say hi to everybody? So Andrea is helping with the cameras today. For the rest of the week, it will be my PhD student, Tim Wheeling. He had his Viva yesterday, and he warned me he would be a little bit late this morning. So just today, Andrea is filling in, and then if you have any issues with the cameras or with the overflow display next door, talk to either Andrea or Tim. All right, I think that's all the things that I was supposed to say. So I want to just introduce two people. Jane Walker is the center manager for the ICMS. So she's helped us from the very beginning when we were writing the application and planning everything. And then starting in January, we've had just immense help from Joel Kerr, who's organized basically everything so that I can just focus on your talks. So please.
So I'm Jane Walker, and I'm the centre manager here. I'm the administrator of the ICMS, and I just wanted to welcome you and to alert you to all the great opportunities that ICMS there is a sheet here that says in very small letters funding opportunities, and that's just outside on the table, and I suggest that you pick it up, read it, and think about how ICMS can help you. So as well as running these week-long workshops, we also do a program called Research in Groups, and David and Monica did that recently, where Monica came to work with David for a few weeks in quiet isolation away from all their day-to-day tasks, and we can help you with funding for that. There are lots of other initiatives that we do. As David said, we are primarily funded by the EPSRC, but we also do a lot to support the mathematical community in the UK, and we're one of 2 centres like this in the UK, the other one being the INI at Cambridge. So we're here to help people do maths in the UK. You don't have to be based in the UK to run a workshop here, but you do need a collaborator in the UK to help you do that. Okay, so please pick this sheet up and find out more about ICMS, and I hope you all have a wonderful week. Jill.
Morning everyone, and welcome back everyone who's here last week. I've just got a few things to run over in terms of housekeeping. Firstly, there is a scheduled fire alarm test on Thursday morning at 11:30. It's just a test, so no action is required. If you hear an alarm at any other time, assume it's real and you will need to evacuate. The evacuation signs are signposted. If you're in here, it's turn left, go through the ICMS offices and down the back stair, and then turn left outside and meet at that lamppost pillar thing that's on Quarter Road. We'll be around, there'll be staff there to help you who will have vests on. I'm based in the ICMS offices, which are just through that glass wall there. If you need anything while you're here, please just ask. I'll be around at breaks. If I'm not there, one of my colleagues can help. Please make yourselves at home while you're here and just ask if you've got any queries. The toilets are at the end of that corridor down there. Obviously there's quite a large number of us in this week, so there are also toilets in the same location on each floor beneath. So just take the stairs down and you'll find them. I think David mentioned the catering. Lunches will be provided in the landing out there where we did registration this morning, but we can go out into the student breakout area. Please just make yourselves at home. When you registered, if you weren't a local, you would have been given a security pass and your name card. You need to use that to swipe in and out. Reception is staffed from 8:30 until 5:30. After that time, you will need to use that to swipe your way out. And we will need these back from you at the end of the week, but I'll remind you of that. For those of you who are here all week, there is the workshop dinner on Wednesday evening at 7 o'clock. That's in the Playfair Library. There's obviously a lot of locals here, so maybe attach yourself to a local. They can show you where to go. It literally is a 5-minute walk, if that, down the road. But I will leave some maps out there, outside, on Wednesday afternoon, so you can see where to go. And there was just one other thing that occurred to me, which I've not listed here, but if anyone needs a certificate of attendance for the week, please just email me and I can get that prepared this week and have them ready for you for collection on Friday. Okay, that's all from me, and I hope you have a good week.
Thank you, Joanne. Thank you, Jen. Sorry, and Dan will be chairing your session.
Dan doesn't know how to raise.
Yes,
You're not using. Okay, well, welcome to everyone, and in the spirit of David's introduction, I'll keep it short. So the first speaker is Catharina Stroppel from the University of Bonn. We'll talk about DAHA actions on fusion rings.
Thank you very much for the invitation. So I will talk about actions of double affine Hecke algebras on fusion rings, and also connections to certain generic Hall algebras. So because I saw that the audience is pretty broad, and many of you work in connection with CQFTs. So I want to start with a good tool to construct CQFTs, at least for three-dimensional things, is the notion of a finite semi-simple
tensor category. Maybe you also want to introduce to use the word orthogonal. So finite just means I have finitely many simple objects, and the famous examples, which will be the basic tools in this talk, are arising from web Q. So this is web Q, where U is UQ of G, and G has a semi-simple complex behavior. And Q is the root of unity. So Q says as primitive root of unity. So and web U means finite dimensional representations in the sense of, so this is the Lustig's version of the quantum group, and I look at finite dimensional representations. So let me start with a little bit of background. So what are objects in this web Q? The basic object in this web Q is the dual Y module, delta lambda. So this is just the following construction. You start, so my representations are over complex numbers. You start with a one-dimensional representation with weight lambda. So lambda is a weight. If you want, you can take it integral. And then I take Holmes over B, that's the Borel. Maybe I leave out the Q, and I induce that to U. So this is, of course, in general not, it's never finite dimensional. And in general, this is, or most of the time, this is 0. It's like for finite dimensional representation for complex semi-simple algebra, you get only something if you take a dominant interval. So these are the dominant intervals. Okay, so now I also can dualize it.
Catharina, not lower than this.
Not lower.
Please.
Yes. So I can dualize it. So this is just the dual of that. Just the vector space dual, and you twist the action by the Chevalier automorphism, and you get a this. Oh no, you don't actually twist. So this is dual Y module, and the other one is the Y module. So when you get that web U is ribbon tensor. So now what I'm interested in is so-called tilting objects. So tilting objects is certain objects which have no self-extensions. So you might also know them from tilting equivalences. And so in this framework, T in web U is tilting if, by definition, it has a delta filtration and a nabla filtration. So by this I mean a filtration by submodules such that the subquotients are of this type, respectively. Characterize guys which have a delta flag as having no x with nablas, and vice versa you can characterize modules which have a nabla flag with no x coming from deltas. You can easily show if you have a tilting module, then a direct summand, and the direct sum of tiltings is again tilting. So facts, tiltings form an additive subcategory of review. And what is even nice is an additive tensor subcategory. And I should call this by name. So that means it's closed under direct sums, direct summands, and tensor products. So this tensor subcategory, this is not totally trivial. So the only proof I know goes back to Anderson and Paradowski. And also they didn't write it in this way, but it uses canonical basis. So it's not totally trivial. In type A, there's an easier proof. So this is in a paper of canonical basis there. So then, if you know like highest weight categories, you can apply the construction from there. What is the classification of indecomposable tiltings? So indecomposable tiltings up to isomorphism.
Catharina, are you already doing rules of unity or it is general?
So I'm doing word of unity.
Always. So the whole lecture.
Yes.
Okay.
Yes. So it's as primitive root of unity. So indecomposable tiltings are just in bijection to the same set as the deltas. So I have a dominant integrate and I have a corresponding indecomposable tilting T lambda, which has the property that it has a delta flag starting at the bottom with this delta lambda, and then you just extend by other ones in the maximum possible way. So this is what they are. And then every other tilting in this T category is just a direct sum of such.
But shouldn't there be finitely indecomposable?
So maybe I should draw a picture. So at the moment, so if this is my dominant Weilchamber, my say SL3 Weilchambers, then
What is T lambda?
T lambda is just the indecomposable tilting corresponding to that, and you construct it by taking delta lambda and then extend as long as possible deltas on the top. So there's a unique maximally possible extension with this delta lambda in the bottom, such that it has no x width from deltas into here. And this is the T lambda. So, and coming back to the question here. So at the moment, my indecomposable tiltings are labeled by the dominant integrate, so it's infinite. I have infinitely many indecomposable. So this is, if you want, this is this T is a category with infinitely many indecomposables. And this is what we don't like. So, therefore, I want to change this. And so, this goes back to, from what I know, again to Anderson and Paradowski. In this framework of quantum groups, but it's a general construction using tensor categories. So I take this tensor category of tiltings and I can just factor out so-called negligible. So what does it mean to factor out negligible? So there's a notion of a quantum trace or trace in a tensor category, or if you want of a trace of an endomorphism in general. So if you take the trace of the identity map from an indecomposable tilting to itself, you ask whether this has trace 0 or not. If it has trace 0, you call it negligible and you factor it out. So that's a general construction to kill some morphisms, but by killing identities, you kill objects. So this is a semi-simple tensor category with finitely many objects, simple objects. There's not finitely many objects, but finitely many simple objects. Okay. So, and of course, you want to know what are these guys. So first I should mention these delta lambdas. These are easy models. They might look complicated, but they're actually easy. So you know character formulas, etc. And they tensor in principle. If your root of unity has a big order, they tensor together exactly like in the classical case of finite dimensional state of the Lie, semi-simple Lie algebra. So these are easy guys to understand, whereas the tilting modules are a bit more complicated. But there's, in these categories, things become somehow similar. So, and this is a result which I found in the paper of Savin, and then in the formulation I give you now, I have it in the joint paper, which will appear soon with my student Geiger. So, namely, T lambda is negligible if and only if lambda is in the set AL. So this depends on L. And this is the following. These are all dominant integral weights such that if I take lambda plus rho is the half sum of positive roots, paired with a maximal root, this is smaller than L fund. And what is L fund? So L fund is equal to L. This is my order of the root of unity if L is odd, and it's L half if L is even. So for me, this is what representation theory is like, because they think of the root of unity being a characteristic of a field often. This is, I think, what topologists prefer. When the root of unity is even, this is what comes up in Chern-Simons theory, etc. And so what?
Negligible or non-negligible? So
Yeah, I would think it's non-negligible.
Oh, not.
That's
Yes, thanks. So, and what is this theta 0? This theta 0, this is either the maximal short root or the maximal long root.
Catharina, so this is the same answer as for reduced category, right? From Q dimension is 0, right? It's the same answer.
It's the same answer. Yes. So it's this or this depending on whether D, so now I'm using the correct cases, where D divides L right or D does not divide L right. So L right will I divide, and what is D? D is the maximal absolute value of the off-diagonal entries of my Catha matrix. So D is, if you want, is 1 in cases A, D, simply Lay's cases. D is 2 in types B, C, F, and D is 3 in types G. So, and this is a bit funny because it connects somehow an affine Y group either in the original root system or in the dual root system. So both things come together. And if you look in the topologist paper, and topologists are usually much more clever than the representation theorists, they tell you the best thing is when 4 divides the root of unity. And so this is this case, and you have to do with the theta short. And usually they restrict to these cases, and everything is nice. And the not so clever representation theorists, they stick to L being odd, and usually, and in particular, D does never, L is odd, and then you have not divisible by 4. Wait. So this is the topologist world, which is nice. And the other one is the representation theory world, and this is bad. So, okay, but we will see this a little bit later, how this comes in.
Catharina, here you have two Q's actually, right? For DC, you have two.
I have one Q at the moment.
Yeah, so it is classical quantum proof,
Yes.
not the case of
Nothing
unequal
fancy.
parameters here, right?
No, only one. And there will be only one. So now, if lambda is in LA, in this fundamental region, so I should maybe draw a picture. So what does this AL mean? So it means we have an extra hyperplane given by this condition here. And then the points in there is AL. So in particular, this quotient has finitely many simples, and the simples are just the tilting modulus T lambda in this quotient. So if lambda is in AL, then my tilting is simple, and it's equal to this in this quotient. And so I call this fusion of the. Okay, so let me do an example, a very easy example. It's a bit misleading because it's too easy. G is SL2. Then in this condition, we have lambda plus rho paired with a simple root alpha is smaller than alpha, because alpha is short and long. And this is, so rho paired with alpha is the Coxeter number. So this means that we have this is smaller or equal lambda prime minus n. So this is the Coxeter number plus 1. and this is 2 in this case. And this is usually called the level in this setup. So it comes from the affine, that's movie side. So what happens in this case? In this case, I have tilting modules labeled by integers. So this is just a times omega 1, tensored in this quotient here. So I put a bar over the tensor product, TB. So the usual tensor product would look something like this. And then everything is killed, where this number is bigger than this k. So kill T's, where C is bigger than k. So if the usual tensor product, you know from SL2 finite dimensional representations, but you kill some of them. And so in this example, it's very easy because you can write down everything explicitly. In general, it's not. So now here are the questions which come up. So first question, what are, I call them Littlewood-Richardson coefficients. So by this I mean, if I tensor T lambda and T mu, I can decompose it because this result is tilting. I can decompose it into T mu's, and I have the coefficient like this. Of course, it depends on L. I put an L here, and I sum over N. So what are these guys? And in the classical situation, if you would put, say, a root of unity to infinity, these are the classical Littlewood-Richardson coefficients. They decompose finite dimensional representations, but here it's a bit more complicated. Second question is, so I have this fusion ring, this one here. I can take the coordinate group of this. It becomes a ring via this tensor product, and you can view this as a quotient of the character of, say, a Lie algebra G. By just taking, say I take the character of the finite dimensional ordinary classical irreducible representation of highest weight lambda, and you send it to the character of delta lambda. They are the same thing. So it's a quotient. And so the question is, what is the kernel? And so there is a paper by Bauknecht. And they do cases A and C, and then there's a paper by Anderson and myself where we do everything except that there's a mistake in type B, which you have to fix. There's a calculation mistake, but otherwise it's correct. The kernel is described, so we can realize this as a commutative ring modulo some ideal. But the question is, can we understand what this ideal is just in a different way apart from calculating? Third question is modularity.
Catharina, but for deltas it is pretty much known, sometimes not maybe in full details, right? Just the evaluation of rules of unity inside while chamber, proper while chamber,
Yes.
right?
Yes.
So it is, here the problem is, but tilde coincides with deltas here.
Yes. So this is, it's really easy. I mean, the character is just, of the delta is just a normal character. Right?
And of course, M's are famous within the NIJK.
Yes, it will come now. So, modularity, so I found this in a paper of Savin. Again, I don't think, it should be much older, but I don't know. So, when is this category rep U modulo? Or this fusion category, when is it modulo? So, if D divides A part, then it's always modulo. If L is odd, it's almost never modulo. So you see there's two differences, and so this, I would say, the topologists are much more clever because they restrict themselves to this case, and they restrict to this. Just 1 second. So there is a, what I make, it's almost, there is an explicit list in this paper of Sabine, which I don't want to write down, but it's just a list by case by case. Yeah?
All this is for L sufficiently large, or
No, L is a primitive, it's just a L,
Like, it doesn't
you
have to
just
be-
fix.
does it have to be bigger than the dual Coxeter number or
So
something?
if
like
it's not bigger than the dual Coxeter number, then you can easily check that this AL is empty, and then your category collapses to 0. So there's nothing. So you better make it bigger than the Coxeter.
Your skin relation is contains q minus q inverse or q minus 1. So like q minus q inverse or q to the 1/2 minus q to the minus 1.
Exactly. It's a half. So what does modular mean? Modular means if I look at the following picture in my tensor table. So this is supposed to be a Hauptfläche. And I label it with T lambda and T mu. And I just read this from bottom to top. This gives me an endomorphism of the identity functor, or the unit object. And so this gives,
I mean, what is it? Of course, it's about counterexamples. They are net modular, right? What you're discussing about.
no, this I just described,
Modularity or
I just described what modular means.
Ah,
So I just want to say what the S matrix is.
What's modular? What's modular?
I say it just now. So if you take this Hauptfläche and you label them by T lambda and T mu, this by reading through it, this gives you an endomorphism of the unit object. So you can define a matrix S, which has entries S lambda mu, where lambda and mu runs through AL. And so this entry, this is the scalar, which is given by this. So this gives you a matrix, and modularity means this thing is invertible. And it's modular, it's not invertible.
but still, gamma O2 is supposed to add here, right? It is just about SO2 is here, maybe not. But normally, gamma O2 normally acts here, right?
Yes. Can I make a comment?
Okay, sure.
I'll make
sure.
a comment much later
Yeah.
because I think at the moment it's confusing.
So basically, all of them are modular, but sometimes you need to go to Congress subgroup.
Yes,
according to-
yes, you can say it like this. So, and then there's the famous Verlinde formula, which expresses this Littlewood-Richardson coefficients, depending on the level, in terms of a S matrix. I just write it like that, as mu sigma divided by S 0 sigma. So, what you should just see in this formula is the coefficient lambda mu mu, so it depends on three things, is a product of these matrix entries, and you should really think of them as I multiply a matrix with another matrix and with a third matrix, and you normalize it. And so this is the explicit formula. Yeah?
This like non-modular case, what are you like? Can you give us a sense of the kind of invisible objects?
Yes, so you can list them, and very often it's just generated by one single object, which is something like a multiple of a omega I. And so it's I can tell you a little bit later where it comes from. What I can say at the moment is, if you know affine Y groups and you look at action of a correct affine Y groups on weights, it picks out the corresponding orbits. And the question is whether every point is in a single orbit or not. Okay, so now what I want to do is I want to give you a model which can compute these fusion coefficients, or Littlewood-Richardson coefficients, in terms of whole algebra. Okay, so I restrict here to the case of SLN. Otherwise, I'm not 100% sure if this thing works, or whether one has to change a little bit. So it's not worked out in general yet. Okay, take labeling of a tilting module in my AL. So this is a weight. So it's of the form mi omega I runs from 1 to n minus 1. So what I do with this, I turn it into lambda hat. This is an affine weight. So weight for the affine, the algebra SLN hat. So it's the sum over mi, but now I runs from 0 to n minus 1. And I just do this because I fixed my root of unity. This m0 is just k minus the sum of mi, I from 1 to n minus 1. So if you look at this condition here, and you reformulate it in these terms, it says that the sum of the mi's is always smaller or equal than m, and I just sum it up with m0 so that I get strictly.
Can you put a lambda 0 or an omega 0 something?
You forgot to put, you have fundamental weights on one side, and you have the sum of integers on the other side.
Yes, thanks. So k is in this case again is what is it, L minus n. This is the level. Okay, so that means what I have then is a affine weight. So this is my affine tilting diagram, where you can think of indicating here m1 and here m3. Okay, so now classically, then I take L lambda tensor V. So this is the natural representation. This determines all the products, all Linwood ridges. So maybe Monica and Arun might not agree with this because they understand the term a little bit different. But in principle, you tensor with V, you understand this, and then you do some sort of geometry forms or something, and you get everything. So this is like the PRE code. So now I want to do the same thing in this fusion setting. So what does it mean to tensor with V? So V is a finite dimensional representation which has its weight epsilon 1 up to epsilon n. When you tensor it with L lambda, you sum lambda with all the epsilon i's, and you check whether this is an allowed weight. And if it is, then it occurs in this sub, otherwise it's not. So now I want to understand what it means to add epsilon I. So if I take a weight, I take an operator, AI, which just takes this weight and adds epsilon I. That's very simple. And you write it in this GLN case. This is lambda plus omega I minus omega I minus 1. So what does it mean? This means in this picture here, I would just take one spot here at the place I minus 1. I move it there, and this is what I call A2. And this is what integral persistence people or physics people would call particle hopping. You hop from one place to the other, you delete your particle and you create it again. Okay? So this moves, say, a particle from place I minus 1 to I. So here's the proposition. This defines an action. So this is actually this curve. This defines an action of the generic Hall algebra on place 0 of this fusion in GLN case. So
you know, the answer is McDonald to coefficients of McDonald to operators, right?
Yeah, to quick.
Unfortunately for minuscular weights, but this is the nature.
Yeah, but you have to quick. This will come. So, what is this generic Hall algebra? I actually don't like the name generic here. This is how they call it. I would rather call it G equals to 0. Q equals to 0 case, where this Q is the Hall algebra Q. It's not the Q which we have. So let me put this in quotation marks. So let me give you the definition of this generic whole algebra. So this goes back to Reinecke in the finite case, and then to Feng, Du, and Zhang in the affine case. Let me first say what is the whole algebra of gamma. So this is an associative algebra structure on the span of isomorphism classes, and you can whatever take Z span, Z span, whatever you want. So in this case I want to take the Z span of representations of gamma, the quiver gamma, over a finite field FQ. So this Q I should circle because it's not our Q from before. It's a finite field, and it becomes the Q for the quantum group. So, but we don't want to have the Q. We want to set Q equals to 0. So we remove this, and so I don't have to say what Q is, and we just take it over, say, algebraically closed field K. And what does change? So what is the algebra structure here?
Sorry, 0 or 1? You just how can you remove Q? Or you need
So I tell you how I remove Q.
One.
So I work with representations of my quiver over an algebraically closed field. Let's say complex
Q
number.
with one
Is it
element is
characteristic
fine,
zero?
but 0.
Characteristic, you can say characteristic 0. Let's say K is.
Okay, characteristic 0.
So, but I have to tell you now how you multiply M and N. So, and this will then be the generic college. Okay? So, what do you do usually? Usually you multiply M and N by counting the number of extensions of the form N on the left, X in the middle, and M on the right. Right? This is what we usually do. Now, this product is just by definition the generic extension of this form. And now I have to say what generic means. And generic means, so you can define it as the extension where you put this X minimal in the sense that it has minimal possible endomorphism range. So let me give you an example how this works in the case of an A2 quiver.
Is it like product and conversion Baron-Move?
It's a product in Baron-Move homology, but you have to remove certain lower terms. So if you do it in Baron-Move homology, you still get somehow pieces which you would usually have a Q coefficient. So, and I want to remove them. But it's something very easy. So let's take this quiver, this dimension vector 1. I can take a representation by putting a lambda here, just a scalar. So if lambda is 0, then it's just the sum of two irreducible representations. If lambda is not 0, it glues together to an extension. And the extension has smaller endomorphism ring than the semi-simple guy, and the extension is the generic one. So this is what you take, and here you can understand why it's called generic. For the generic value of lambda, you get this extension, and there's a unique one. And if you think in terms of orbits, the orbit for lambda not 0, the closure of this contains the orbit for 0. And you put an ordering, so this is the generic case, and this is the semi-simple case, and so you put an ordering on your representations by saying this thing is smaller than this orbit if this orbit is in the closure of this. And then it's the minimal extension in this orbit. So it's a minimal extension in the ordering where O is inside smaller or equal lambda prime. O is smaller or equal O prime if O prime is contained in O.
Catharina, it is elliptical algebra when Q equals T, right? What you discussed. What do I mean?
No idea.
Late, maybe.
No, I think this should be much easier.
Q equals 0, right?
So it's a unique one, and you can also look, if you look at the moduli space of all such extensions, then it forms a unique dense orbit. So, okay, so now let's do let's do this explicitly. What is this algebra in this case? So it has generators which I call AI, given by the classes of the simple representations of SI. So I runs through the points of my quiver. This, and here are the relations. So they commute if they are not connected. So you always calculate modulo n, and they have these sort of relations, which are some sort of general pair relations. So you can take a 2-parameter version of the quantum group. This parameter is Q and R, and if you specialize it correctly, 1 to 0 and the other one to Q inverse, then you get these ones. And I call this with Christian Koch, we call this affine lactic algebra.
Catharina, if this Q goes to 0, then it must be periodic, exactly periodic relations from classical McDonald's periodic spherical functions. If it is Q goes to 0, right?
This has nothing to do with my fusion thing at the moment. It's not the characters. So it acts on fusion. So it's on a different level. So this is called affine lactic algebra because the lactic algebra was introduced by Lascaux and it had similar relations except that it was not on the circle. Okay, so now what we can do is we can define, and so this is what Christian Koch and me do, or did. We define elementary symmetric polynomials in this AR, in this A's, by just the usual formulas. I take the product over all AI's. I is in a subset I, and this subset is inside 0 and n minus 1, and of cardinality R. So it's exactly the same definition as I usually have, but because these things only commute when they are far apart, I have to be careful with the ordering and I make it cyclically. And this only causes problems when I have no gaps, I don't know where to stop. So when I have the product over all of them, then I just define this. So you have them here, so for each point you have an AI. And so for instance, so I want to have first the 1 and then the 2 and not this guy. So it should go in the cyclic order.
R is less than n or something.
Say again?
R is less than n. You don't have too many. You don't
Ah,
go
yes.
down
So
one.
in this case, R is less than n. So R is between 0 and n. And if I have n, I set it to 1.
It's also important where you start.
So it's not important where you start because when you have different chunks, say these guys occur and these guys occur, because of this relation, they commute. So the parts commute. You just have to be in order when they are made.
Before you quotient the relation E and A equals 1, is E and A already central in the...
It's not central.
It's not central, so
No.
you actually really...
It's not central. I was hoping it's central. It's not.
Maybe it's Q central or something.
I don't know. I couldn't get anything reasonable. So this generalizes the construction of green, Fomin and green, where they did a similar thing for the not affine aggregations. So, and now here's the theorem. So, yes. First, there exists a common eigenbasis for the action of the ERs. On K0 of Q. So they act on that, and it's a common eigenbasis. So in particular, they commute. So if they commute, I can define sure functions depending on A as in the usual formula. This is determinant of E lambda I transpose minus I plus j of a. So this is defined. And so we proved that there's a common eigenbasis using some BT-Ansatz techniques, using this integrable systems model, which is somehow hopping of particles.
You must have some intertwining operators when you like to much simpler.
So
Because of the origin, there are some intertwining operators.
so think of these ERs.
That answers is the last escape, right? If you have nothing else, then you
So
use that
the
answer.
sum of the ERAs is a transform matrix, but you should think of them as polynomials in the Y in the DAHA.
So I want to check that I have the action correct.
Yes.
So you take like a tilting for lambda and you act by the AI there by adding epsilon i's, but you'll do this for this product. With these
Oh yes.
and
So I identify lambda with the tilting, and then you just act by this very easy moving, and this is how you act. And so in particular, everything is defined over integers. It's like, and I should have said this to you. What I construct here is really a crystal for this space SK C to the N, and these are Kashiwara's crystal operators. So it sends a basis vector to a basis vector or to zero. If a particle continues. Okay, so number 3 is if I take lambda in a L. I should have said what S lambda is. No, this makes sense. This makes sense. But if I take lambda in a L, I can associate to the partition lambda. A partition where lambda I is equal to lambda I is defined by lambda I minus I plus 1 is equal to mi. So this is just the usual calculation between the omega and the epsilon basis. And so here's the main theorem, or the main part of the theorem. And then when I take the sure polynomial acting on mu, so mu is an element in A L, but I view this as such a particle configuration, then I get a sum of particle configurations mu, and the coefficient is exactly fusion. So let me do one simple example. So let's say I want to compute for SL2 T mu tensored with T1. So that's a natural extension. So now let's draw mu. So mu is m1 times omega 1. So I put this on my affine figure. Vertex 1, vertex 0. I have my level k. So I put here m0. And m0 is k minus m1. So now I want to act this S1a, this corresponds to this guy, on this mu. But S1a is of course the same thing as elementary symmetric function, E1 of A. So an E1 is just by definition A1 plus A2 acting on mu. So this, 0, whatever, you take everything model n. So this A1 moves the particle from here to here, and the A0 does it there. So what do I get? I get, so this moves from left to right, plus from right to left. But this one I can only do if n0 is at least 1. So that means if mu1, m1 is smaller than k, I get this. Otherwise this is not possible. And only this works. And so this is if m1 is equal. And so this is exactly what we saw before. You just tensor as in the normal way. But if you get out of your allowed range, you just kill the tensor. And so. Okay, so and I should remark the phase change from the T lambda basis in this fusion ring to the eigenbasis is the S matrix. And then if you remove it, if you look back at this Berliner formula with this sum of the three guys, what this formula says is you have one base change to the eigenbasis, then you calculate in the eigenbasis, which is very easy, and you base change back, and in this way we can compute this product. But the interesting thing which I find important here is that this construction doesn't see the level, so it's always the same algebra which acts, and you just put the level on the space where you act.
Didn't you have that the S matrix was quite often non-invertible?
Yes, so I just wanted to say something, because I'm cheating here. So I should add here if L is even. And otherwise, I have a problem. And I didn't realize this for a long time, because I thought everything is fine, but I wasn't really carefully reading Ivan's book, because he put Q a half instead of Q. And so if you normalize it wrongly, then you don't see the difference in even and odd. So it's the S matrix when I replace Q by Q to the half. And so I couldn't see that it's not the S matrix. But in the case where L is odd, it's you have
Then
to
it
take
appears,
it.
this difference between even and odd appears in some kind of a long story about main sector of Berlin, the algebras, right? Perfect representation, I call it perfect representation.
No, I don't want to do perfect
What do you
representation.
mean?
So I just say so the base change is the S matrix if L is even, and otherwise it has entries, or always entries, certain Schur functions in L roots of unities. And if I would replace this L by L bind, then it would be the S matrix. So it's just somehow a parameter switch from root of unity psi to psi half. But of course it should not be invertible in Europe. But this base change matrix still exists, and it is of course invertible. Okay, good.
So you prefer twisted setting. It is called twisted setting, right? A special story about the DC, right? But then we'll discuss it.
You have to, no, we should discuss it later. I don't know what we need. So, okay, now I want to refer to Monica's talk last week. So what do I have now? I have a ring, where I have some action of some operators. I diagonalize it, and I have a base change, a nice base change, and the eigenvalues, which is in this, I didn't write this with the eigenvalues, but the base change matrix contains Schur functions in L's root of unities, ordinary Schur functions, and what you also can check is that the eigenvalues here are elementary symmetric functions in roots of unities. So ordinary elementary symmetric functions in roots of unities. And this looks very much like McDonald polynomials specialized at Q at T equals to something. And this is how it's connected with DAHA actions. So I take my SLN and I can construct a DAHA for this. So this is as a vector space. It's a so I do it over C, but in principle everything which we do here. No, I think I should do it over C. Take this guy and just imagine group algebra and the vice. So as a vector space it's this. These three things are sub-algebras, and this here forms affine Hecke algebra, and this here also forms an affine Hecke algebra, but you also have more complicated relations between these x's and the y's, which I don't know to write down. So
last week I was calling it GL, DAHA, not SL.
okay, it depends. I didn't tell you what the x's are.
Yeah.
And I don't want to. I actually want to use SMU, and because Ivan is here, I should not cheat. So, if I have this, I take a polynomial representation. P, which is the induced one from this AHA to DAHA. There is this trivial representation. And of course, I should have said everything depends on parameters. To DAHA. So, and this is as a vector space. Okay, and now here you can define non-symmetric McDonald's polynomials, etc. But I want to do something which is symmetric because I want to work with characters. So to make it symmetric, I look at the following idempotent. So it's the trivial idempotent if you want. It's t to the length of w half w. So these are the so because this is not really the symmetric group but the Hecke algebra. So these are the generated in the Hecke algebra. I sum over all symmetric group elements. Yes, and then I make an idempotent out of it. So this is sum over t to the length of w. I think this should be it. So, and this makes sense. So this is trivial idempotent. And this idempotent makes sense if my root of unity, my else root of unity, this L is bigger or equal n. And this is what we needed anyway to have a non-empty fundamental algebra. So this makes sense even for t being a root of unity. And now I want to set t equals to q equals to this as well. So this means I get rid of all the parameters more or less. And then here's the theorem. So what I have a polynomial representation which up to this plus minus exponent of the axis you should see as a polynomial ring. And I want to make it symmetric now to talk about characters and get a character ring. So this is together with Vincent Geiger. So first thing is, if I take E times this polynomial representation P, because this is a DAHA module, so this makes sense, then this is just x1 plus minus 1, xn plus minus 1 is n, and maybe I write w, and w is n. So, and this is
this is well known, right? It is not well known.
Yeah, this is well known. Yeah, this is well known. That's an easy calculation. So this is just an E DAHA E module. So yeah, I state a few things which are well known. Also, the second one I couldn't find in the literature, so you should give me a reference. There is a natural bilinear form, symmetric bilinear form. On P, which is invariant with the action of the DAHA in the sense that if I move it to a DAHA element to the other side and twist it with swapping x with y and keeping the symmetric group part, so it doesn't change, so it's invariant form.
This is called evaluation form. Oh,
yes.
Sorry, not exactly evaluation, McDonald's, canonical
yes.
McDonald's inner product.
So this is exactly your inner product.
There are two of them, right? This is McDonald's, one pairing with mu function.
This is McDonald's. So, and so this is Church. And I define radical, let radical be this radical. So, and if you look in Geometric's book, this form and the radical was used to define irreducible representation for DAHA. Now, what I want to do spherical, And in particular, I want to be in this setting. And I think this is probably not considered. So, and this radical is compatible with this idempotent in the sense that E times radical is the invariance of the radical, and this is the same thing as the radical restricted to the invariant polynomials. So I don't necessarily claim that this is, I mean, this is definitely obvious and this form is interactive, but the point is I want to restrict
the fundamental theorem here, if you use evaluation form, not this particular one, evaluation, then it is the irreducibility of the quotient, this fundamental theorem in the business, right? If you consider by the
yes, but I want to have it for these parameters.
Yes.
This is important. So exactly this is what comes now, and I define this as E times P modulo E radical. And the statement is that this is an irreducible DAHA module if
again, generally this can be a little bit bigger, but if you divide by evaluation form, by the radical, the fundamental theorem is irreducible. For arbitrary systems, no restrictions. Yeah.
You have spherical DAHA there, right?
Oh, spherical, yes. So now the fourth statement is I have this E polynomial, I have E radical, and I have the quotient n. Now on the other side, I have symmetric polynomials, and this you should think as the character ring of my linear algebra. Now this quotients to K0 of fusion, and it has a kernel K. And this kernel, this is exactly determining how this fusion ring is viewed as a quotient of the character ring. So the statement is I have a map here, which is the obvious inclusion from here into that. It induces a map here, and it induces an isomorphism. And the point of this isomorphism is that the eigenbasis for these E's is mapped to the y plus minus eigenbasis on the back side. So, and the eigenvalues become eigenvalues for them. And so these are just sure functions in roots of unities. So these are just Macdonald polynomials specialized in this very special case. They are of course easy, but they should be easy.
I think they're not too easy.
But I mean, they should be easy in the sense that I just work with the character, with nothing is different. So, and maybe I should say in 1 second what happens in other cases.
Catharina, just a remark, it will take 30 seconds, maybe 20 seconds. How the identification goes. So surprisingly, through this awful formula S divided by S, which is so much stupid mathematically, but it works. I use Katz-Peterson here, right, and identify my theorem with them through Katz-Peterson. Katz-Peterson for arbitrary systems, right? So identification with fusion is done when Q equals T. So we use Katz-Peterson advances paper here, right, for explicit calculation of S operator. So I use my formula for S operator, as you mentioned, characters at roots of unity, roughly speaking, right?
Yeah, but I really want to have this thing on the nose. I want to have this space on the nose, and nothing bigger, nothing smaller.
So this is general theorem for arbitrary system identification with fusion is done here, right, when Q equals T.
Yeah, but I want to identify with this particular fusion ring coming from the quantum group.
Yes. This is done thanks to Katz-Peterson, their fundamental paper in advance.
Oh, okay, we have to discuss it because I claim there are some problems at a few places. So because if you generalize this to other types, then you can still construct this module here.
Yes, it will be bigger. It will be
and then it will be bigger, exactly.
Yes,
and
yes,
this
because
is
if
exactly
the definition is not good, you need to consider evaluation pairing, then it will be exactly reducible. A different some kind of pairing in Macdonald theory, actually, right?
Yes, and what you get is that you get something. So this thing would be smaller than this guy, and the reason is because this is then not necessarily modular this fusion ring. So you take a quotient of this fusion ring or the fusion category, and then the result is modular, and then it identifies with this irreducible modular. And this is for any type, and you can see on the nose the connection with this affine Y group and this modularity condition in the strip of Savini. So there is, I cannot match it. This cuts with what is Katz-Peterson formula on the nose.
Sorry, not many know this fantastic paper in advance, very fantastic paper in advance. Katz-Peterson here, right?
Yeah, but I cannot match it, and the reason is because I don't take the Y group, which is the affine Y group, but a slightly different Y group, and then you can see exactly the correspondence with Savini's table with the non-modularity. So we have to discuss, but I think one has to look at a few cases. Okay, this one I want to see.
Does anybody else have any questions?
You not me, right?
Yes.
So here at the bottom, you identified the action of these operators elementary in AI with the Y's. What acts as the X's on K0 fusion?
Oh, I don't know the formula by heart. It's something complicated.
Oh, but is it something meaningful to the patient theoretically?
I didn't know. No, I don't think so. I have formulas, but I couldn't see anything.
Then 3 seconds. Just near this theorem, we will discuss. Put nil data. Near this theorem, nil data. I will explain during the lunch.
Okay, where do I have to put nil?
So there, we found some formulas, not exactly this particular setting, in the story about nil data, which is smaller than data. No, here, theorem. Your theorem, right? So surprisingly, we saw something. I was supposed to recognize it long ago, but I only now I see. Nil, it is called nil, 2 times, nil. It is smaller than data, right? But anyway, I'll explain.
But you have to tell me about it.
Oh yeah, sure. I was supposed to, right? But I see it only now.
What are the dimension of this K0? It's like n power.
So in type
plus
A,
1.
it's just
n plus
n
1
plus
power.
k choose k.
Uh-huh.
And in other types, it's not such a nice formula. We can count. We make a bijection in other types with a basis here and a basis on the other side. But we don't have a closed formula. It's not a counting.
And for m, what's the dimension of m?
So in type A, it's n plus k.
But there is a segment base, so I would say.
So actually, if I would work with GLN instead of SLN, then this problem with this even and odd disappears. And it's much nicer, and it's the same thing as quantum cohomology with Mayer.
Yes.
So you can start this commuting elements in this non-commutative algebra, and this commutative subalgebra has a pairing.
Yes.
So is also pairing on this non-commutative algebra?
I don't think so. No.
Yes. Evaluation definitely, right? With non-linear product, some degenerations can happen. But this is I mean, data, not
It's not an obvious one. We only defined it on the
The question is that this evaluation of
I will
adjoint A adjoint times B always the same, right? For arbitrary operators. You need only involution here and evaluation function.
So Monica wanted to ask the first question.
That's okay, I'll ask you in the break.
No, you can ask now. You should
I was going to say that when T and Q are roots of unity, so, is it obvious? I mean, you modify by the radical, but is it obvious you have a basis of Y eigenvectors?
I have to be careful what I say, but I think it's not obvious, and we just had to calculate that this exists, and we also had to calculate it as the right size. I don't have any tricks, but maybe I get thoughts now.
I never even, I didn't understand. When T is Q,
yes,
that's somehow very special.
This is very
The
special.
existence of these eigenbases. So
This is
it
very
obvious
special.
if you think about t equal q first, and then root of unity?
So we tried to do t equals to q first, and then we couldn't get enough finite dimensional representations. So we really need this root of unity. And when you look at the calculations, you use them to have root of unity. A similar thing happens also for when you go to the rational Chladni algebra. You just don't have enough finite dimensional representations.
Any other questions?
So you get like a nice eigenbasis when t is equal to q, even if it's not finite dimensional. Can you produce many y eigenvalues in that for the number representation?
You can produce many eigenvalues. So if my calculation is correct, it's not necessarily semi-simple. So which we also didn't like. We produced eigenbasis, but because we couldn't get enough eigenvalues, we just stopped.
All right, well, let's thank Catharina again. We'll have a short break and resume at 11:50.